Welcome. This is a new module. This is an elective module, so there are the first six modules, these are mandatory. The elective module, you just select the module that you are interested in and you are doing. And this module about Monte Carlo simulation, one of the students at the beginning of the semester, he mentions that he want to learn about cost estimation. So cost estimation can fit in this course, for example, under computer simulation, where you do like probabilistic cost estimation. So I'm providing this elective module. I'm also providing another elective module, regression analysis, and so on. Okay, because this is like it's common and you might use it in other courses or in your project or whatever. Okay, so let's just get started. These are some references which you can check out, or any similar book you have if you want to learn more or practice more. This module so far has one lesson, which is Monte Carlo simulation for cost estimation. So I will introduce Monte Carlo simulation, and then I will apply to calculate like a farm profit. So again, this is just like an example that everyone could understand. Uh, your application could be different. Your application could be an construction project. It could be a consultancy project, in environmental, in water. It could be whatever that project is. It could be ones, tens of hundreds of dollars, or like hundreds of millions of dollars. Like, so the techniques that it's basically like you can use this techniques for various things. So I will just show to calculate the profit of a farm. So for a profit, you have some cost item which could be uncertain, and then you have some revenue item which could be also uncertain, and the profit, that would be your revenue minus the cost, that will give you your profit. I will do this with Python, but I will show you also how to do this with Excel. There are some commercial, or could be also non-commercial software that you can use with Excel, like if you don't like to use Python to do this probabilistic course estimation. Again, this is extra and optional, because this course is really not about using a certain software. It's more about learning the basic concept and technique, which you can later apply on your own, using a software, using Python, using whatever you want to use. Okay, so I will show you both. Okay, let's start with our only, like, our lesson, Monte Carlo estimation, Monte Carlo simulation for cost estimation. And that is part uh, one, which is probabilistic estimation. Yeah. So what is so basically what is Monte Carlo, like, before even so that so Monte Carlo, this is a mathematical concept that use random sampling to predict possible outcomes. So it comes from the name of the city Monte Carlo in Monaco in Europe, and it has gambling industry similar to Las Vegas. So that's why this method got its name from, because gambling, it has to do with randomness. Like, for example, like you throw a dice, you don't know which outcome you will get. You know the possible outcomes. You can get 1, 2, 3, 4, 5, 6. You're not going to get 1.5, for example, or you're not going to get 7. You know this, but you don't know which one. You know, I'm going to get 1, I'm going to get 2. So you don't know the possible outcome. And that's from this randomness, that's the word like Monte Carlo simulation is. So basically, it is a mathematical technique for random sampling. And you can do this to do probabilistic cost estimate. So what is a probabilistic cost estimate? That's different than a deterministic cost estimate. So a deterministic estimate, like you have a project, you have several items in your project, you add them up, that will give you one value, which is a deterministic estimate. It's just one value. Versus a probabilistic estimate, You have your items in your project, and each item is uncertain, and I could describe my uncertainty about each item differently. And then I take different realization. I take multiple sample, and then at the end, I'm not going to get one number as in the deterministic cost estimate, but I will get a distribution that has like a mean, that has a minimum, that has a maximum, that has a standard deviation if it's like follow a normal distribution, or it could has other characteristics. So basically, I don't only get one value, I get a distribution of value, and once I see like my possible outcomes, then I can make informed decision whether I will like overrun the budget, whether I'll be below the budget, what are the main drivers that drive this cost, for example, and that drive my uncertainty, not drive the cost. Yeah, so I can reduce my uncertainty. So basically, that is what we will be doing in this lesson. Yeah. So let's just get started. So by the end of this video, you should be able to describe the steps in Monte Carlo simulation, and you should be able to identify probability distribution for different input variables. So different input variables like so a cost item, you are uncertain about this cost item in a certain way, and we will see like how based on the type of uncertainty, or like the how you are uncertain about this item, how you can describe this, like which probability distribution would suit your type of uncertainty. Okay, so let's just get started. So this is the steps for Monte Carlo simulation with application to cost estimate. Uh, Again, these are like 6 steps. The first step is to identify key cost driver. So here is just an example. So you could have your cost driver, you could have like 10 of them, maybe 7 of them are uncertain, are like deterministic, are not uncertain. Like you have a fixed value for them. For example, like taxes or maintenance fee or whatever. These are fixed values that are not certain. But there could be other items that could be uncertain, like material, for example. Like so, your uncertainty about the material, uh, certain cost, like the material cost, for example. So this material cost, for example, could be not necessarily cost. It could be like the material quantity. It could be material uh, waste or whatever. Yeah, so it does not necessarily need to be the cost, but here I'm just keeping it simple, like just the cost. So you have like a nominal cost. Nominal cost is like an adjustable cost. So your nominal cost for this is like 100, for example, but you are uncertain about this because like the material cost is like the nominal cost is 100, but it could go up or it could go down. Similarly, for labor cost, like the nominal cost is 100. So like you hire a labor, you give him like $100 an hour, for example, or whatever. I mean, whatever, yeah. But again, this could be go up or go down, yeah. Similarly with equipment. So these are the 3 key cost drivers that I identified. And again, the focus here is not like how to identify key cost drivers. That would be topic specific. So you will learn this in a separate course about cost estimation and with a specific application. So that in that case, they will tell you, okay, this is, for example, like the different drivers, and this is the typical uncertainty about these drivers and how to deal with each uncertainty. Here is just the focus is more on main concept. Yeah. So here I can just say, for the sake of argument, uh, for my, let's say, like equipment cost, like this guy here, I will model this, or my uncertainty about this is uniform. What does it mean uniform? So it goes like all the way from here 20 to 100. So this means that this equipment cost could be like as low as 20, it could be as high as 100. Which one is it? I don't know. And that's why I give this uniform distribution. So the 20, the fact that I could get this equipment for 20 or Unity, they have equal probability because I don't know really. I don't know if I will get it for 20 or for 40 or for 60 or for 80. All of these, I don't think that anyone has a higher probability than another. So in that case, you identify a uniform distribution. Yeah. Now let's look at the second one, like labor cost. For the labor cost, I now have a different uncertainty, because I know that the minimum labor cost that I could get, it could be like 60. The maximum labor cost I could get is like 140. It will not be less than this. It will not be more than this. Same as here. But here I have an extra piece of information that the most likely cost will be around 80. Something here. Yeah. So that's the most likely cost will be around like 80 here. So now I know that like it's most likely will be around 80. That is the one that has the highest probability, but it could be as low as 60. It could be as high as 40. But these ones has very low probability. So this is the probability density. Okay. Now let's look at this, guys. The material. Okay. So now I have a certain material. I know that the mean cost of this material will be around here. So that's like around 100. So this material will be around 100, but it follow a normal distribution. It could be very low or very high, but most probably it will be like around, or this not most probably, this is the high probability is would be like around the mean here, around 100, but it could vary uh, significantly, yeah, and it could vary like this is kind of it does not like this tail could go to infinity, and this tail here could go also to infinity, which might not be realistic assumption, and I will talk later about this and how to, if you want to use a normal distribution, how to make it realistic to avoid like going to like very high value or very low values. Okay, but anyway, so okay, so what? So I now I know my uncertainty, yeah. So I know like I have like these three uncertain items, yeah. And for these three uncertain items, I can describe my uncertainty about each of these guys. So here, for this guy, it's uniform. For this guy is triangular because I know the minimum and the maximum and like the most likely. For this guy, it's normal because I know like this is the most likely, but then it could like follow a normal distribution. So what? So now here comes the role of Monte Carlo. So what Monte Carlo will do is that it will draw random samples from these distributions. So here, this is my distribution. Let me just like, draw a random sample. So here is a random sample. Okay, so what is this value? So this value here is about 30. So for this guy, I got like 30. And like for the labor, like this red guy, I'll just draw a random sample here. So my random sample came here at like 101. Okay. And for the material, I will just draw a random sample. So my random sample is here around like 62. Yeah. So this is just like called like one realization, which is like you draw a random sample and then you calculate the cost. So you calculate the cost. So here, like you see, if I calculated my nominal cost or like my baseline cost, here is about 100, 150. So my nominal cost is 250. For this sample or for this realization, the cost would be 163 plus 30. So that would be 193, for example. Yeah. So that is just one sample. I just draw one sample. So from each input, I take a sample, I add the cost. So now my cost for this realization or for this sample is like 193. And so on and so forth. I just keep taking many samples. So you see here, this is just sampling. So here I'm sampling like the green guy. So I got like a value of like, I don't know, whatever, 40 something. I sampled like the red guy, I get a value of 80 something here. This is for my first sample. And then I value the blue guy, I get this value. For my second sample, this is the green guy, this is the orange guy. So you keep just doing this samples or this iteration. You keep doing it successively. Like you generally, like for Monte Carlo to converge, you need to do this like thousands of times, typically. And I will show you later more details about this. Okay, but anyway, so you take a sample from each of these distribution, and then after you take a sample from this distribution, you calculate your total cost. Yeah. So here, for example, this would be the progress of my total cost. So like my first one was 193 or whatever this number is. Remember, all this is random. So if I run this again, I will get a different like a curve. Like it will that fluctuation would look differently, but they will have the same statistics, same statistical properties, or same underlying statistics behind them. But it would be like different each time. Okay, so basically, like, so I have, like, for example, for my first iteration, my cost was around 230. For my second iteration, it was around 100, 200, like 20. See here, this iteration is like above 325. This iteration here is above 125. But like you see, these guys are not many of them. Like, see, this guy is not many of them. This guy is not many of them. Most of them are here. So can I just convert this to a different view where I will see the frequency where most of the costs are? Yes. So basically, this is your forecast. This is your Monte Carlo forecast where you show the frequency of these cost estimate. Like, so this guy, for example, is 155. Like 100, like, see, this small guy has very low frequency. Like this guy here, like above 325, like 350, it has very low frequency, but most of them are here, which means that remember, my nominal cost was like 250. And like from this simulation, actually, I was kind of lucky because I got like my median, or like um, my mean cost is around my normal cost. Yeah. But again, this is just a mean cost. Like, my project could cost me as less as like 150, but this has very low probability, and my project could cost me as high as 350, but again, this has very low probability. Most probably my project will cost me around 250. That's most probable. That is the one that has the highest probability value. And which means that we did like a good job in our initial cost estimate, because it's close to our most probable cost. But then I could convert this to calculate, for example, so now I analyzed the cost distribution. So now I don't have one value like 250. I have a distribution. It's not like I'm reporting, like, so your supervisor will tell you how much this project will cost. So here you'll tell him it costs 250. Here you'll tell him it could cost as low as 150. It could cost as high as 350. Most probably it will cost me like 250. So if he asked you, okay, what is the likelihood that we will exceed budget or be under budget, like this 250 budget, like, can you answer this question? Yes. So you can inform decision by using this like cumulative probability. So here's a cumulative probability. I have here my 150, I have here my 350. What is the probability that this cost will exceed like 150? So you see here the probability of this guy is almost zero. So what is the probability that it will exceed 150? It's like 100%. So I'm 100% certain that that thing will cost me above like $150. What is the probability that it will exceed? Because you see here, this is the zero probability, this is the 100%. What is the probability or the likelihood that this project will exceed like 350? So the probability that it will exceed 350, I have one here, is like zero. So I have 100% probability or likelihood that I will exceed 150. I have zero probability that I will exceed 350. But for my nominal cost, for the 250, what is the probability of this nominal cost? So if I looked at the probability of this nominal cost, it's about like here, like 45%. So I have a 45% probability that I will be at the nominal cost. What is the probability that I will exceed like this 250? It's about 55% probability. So I have about 55% probability that I will exceed this nominal cost of like 250. Where do we want to stand on this curve? Well, that's up to the decision maker, like whether they are accepting to take like high risk or they are like accepted to take low risk. So this would be like high risk here, that would be low risk here. Because if I budgeted this thing and I think it cost me 250, which is only have very low probability, like 10%, and I run over budget, then that could be a problem. Here, if I put my cost here like 300, I might not be competitive. I mean, I'm here at very high like confidence that I have a high probability that I'm not going to exceed this cost, but I might be uh, not competitive. Again, this is not a course estimation course. Like, so don't listen to me when I give you like just focus on the main concept of Monte Carlo, not on the specific of like cost estimation, because the specific of cost estimation you will like, and which degree of risk you are willing to take, which degree of risk you are not willing to take, you will learn this thing in other courses, yeah. But here is just focus on the main concepts. Okay, so let's just look at this in more detail. So here's you identify the key cost driver, and that would be project specific, and that would be like depending on your project you would know which are your cost driver, which that are uncertain and which one are uncertain. But let's look at like these other steps in detail. So let's look at the probability distribution and how to select which probability distribution for what type of uncertainty that you have, yeah. So before we do this, let's just talk about prob- oops uh, let's just oh let's just okay, that was from my previous recording because I usually don't get it right from the first time, but anyway, I cannot erase it now. I hope I don't have many of it. Okay, so basically here this is like a standard normal, and this is standard normal. Like, so what is a probability distribution? So the x-axis represents the possible value. So here this could go from 0 to all the way to negative infinity, and here this could go from 0 all the way to positive infinity. Again, I'm just plotting until like here. But where most, like, let's say we have 100 guys here, yeah, most of these guys, yeah, will be around here in this area here, yeah, that was most of like this guy will be, so that would be around 68 of them. So from here to here, if I have 100 guy, 68 of this guy will be here. And what, like in this bigger area, yeah, in this bigger area, like 94% of my guy will be here. So this is called the mean value, like what you see here. This is like called like the mean value, and this is called like 1 sigma, yeah. And this would be like 2 sigma, another sigma, and that would be like a third sigma, and that would be like a fourth sigma, which I'm not plotting here, like number 4, for example, yeah, fourth sigma, yeah. What does this mean? Like, what does this sigma here is like standard deviation. Standard deviation means that like if I have 100 guy here, at one standard deviation, I will have most like about 68 like here at one standard deviation to the left and to the right, like +1, and here like this would be -1 standard deviation, and that would be +1 standard deviation. So in this range I will have about like 68 of my samples would be here. At 2 standard deviation I will have about 95% of my sample. At 3 standard deviation, I will have like 99% of my sample. At 4 standard deviation, that number will be like, so for example, let me show you like even a better example. Like, let's say I have 10,000 guys here, yeah. So 10,000 guys, and I'm looking like, so like this 10,000 guys. So this 10,000 guys, like about in this region here, yeah, and like the region of the 3 sigma, you will have 973 of them would be like in this region, and only the remaining, which is 727. So the remaining, like these 27, would be like in this region and in this region. So most of them would be here, and like only few of them would be out of here. And this came actually from like the analogy of, like, for example, if you have, like, let's say a drunk person here, yeah. So if you have a drunk person here, and like this drunk person, he's only allowed to move either to the left or to the right. So what he will do, like a random walker, that's called like a random walker. So this random walker, he will, like, let's say, go to the left. Yeah, that's how the random walker will do. And then maybe he will go again to the left. But then it's all random. Yeah, he's a random walker. But then he will go to the right, and then he will go again to the right, and then he will go to the right, and then he will go to the left, and then he will go again to the left, and then maybe it's random. He will go to the right, and then he will go to the left again, and he will go to the left again, and he will go to the left again, but then he will go back to the right, and then he will go to the left again, and then in the next step he will go to the right. So you see, like this guy, because he's a random walker, he will just keep fluctuating from here to here, from here to here, to here, to here, to here, to here. He will not go far away. And that's why, if you, as I told you, like if you have like 10,000 like random walkers here, most of them, like 60% of them would be like, will fall in this region. About like 95% of them will fall in this region. 99.9% will fall at 3 sigma. 4 sigma, you will only have, if you consider 4 sigma, you will only have very few numbers, yeah, of them, like who will make it all the way to 4, 5, 6, or 7 or sigma, yeah. That's basically the idea of this probability distribution. But what you need to learn, for example, from this probability distribution, this is the mean value of the distribution. So you have a mean value, like it's called like mu, and you have like standard deviation. And this mean value basically tells you the value, like, so this value here is the high most likely value. Okay, and then this is one standard deviation from this value, means that I have 68% probability, if I'm considering like that, I will be at like this sigma here, whatever that sigma is. So like, let's say your mu is 80 and your sigma is 5, like, or 20, yeah, which means that I have like here, let's take an example. So this is an example for a normal distribution. So let's say my labor cost, I'm I'm thinking that like my labor cost most probably it will be like at $80. Yeah, that is the highest probability. That's the highest likelihood. But it has a standard deviation, like 1 sigma of 20. So my 1 sigma here, so that would be, so this is 80, that would be like my 1 sigma and my sigma plus. So it could be like with this likelihood, it could be 60 or it could be 100. Like at 2 sigma, like if I consider 2 sigma, it would be like 40, and here at 2 sigma, it would be like 120, yeah? If I consider like 3 sigma, it would be like 20, if that is realistic, and here it would be like, for example, so this is like 2 sigma, this is like 3 sigma, that would be 140, yeah? But again, this one has very low probability, as you see here. Like as you go down here, this has very low probability. So what is the probability that my labor cost will be like 20? Is very low. What is the probability my labor cost will be above 140? It is very low. What is the probability that my labor cost will be 80? That is the highest probability. That's the most likely value that I can, if I want to use this type of distribution, yeah, for to describe my random variable. So here, this is an example like for normal distribution. So here, this is a normal distribution. The mean is 80 and the standard deviation is 20. So this is the mean, and like here's your one standard deviation. So you see this one is wide. Why? Because I have my uncertainty here is very high. Like my one standard deviation is like very high, versus this guy here is narrow. Why? Because my standard deviation is 5. So I know that like this labor will be at 80, but it could vary. It could be like 75 or it could be like 85. That's my one standard deviation. If I will consider 2 standard deviation, that will be like 70 and that would be like 90. And if I will consider 3 standard deviations, that would be 65 and that would be 95. So for this labor cost, if I have like smaller standard deviation, here I'm saying like this goal would be most probably from 60 to 65. Now, if I don't want to, remember, Monte Carlo does random sampling. So never know, like although what this has very extremely small probability, like the probability could be like 1 over a million, but you could get this sample because it's random sample. Although it has a low probability, it will only maybe occur rarely. But if you want to use, for example, minimum distribution and make it realistic, what you can do, you can truncation, like you can do truncation. So what I'm doing here, I'm doing a minimum distribution. I'm saying that like I have a truncated normal. So my truncated normal is, I'm saying my labor cost is most probably will be like around 80 with a standard deviation of 5, but I want to truncate this value to 50 and 95. So because most probably I will not get a labor less than 50, and most probably if I get a labor more than 95, I'm not going to hire him. I will seek another alternative. So what you can do here, you can do just, you can still use a normal distribution with this like truncation. So this is called the truncated normal. So this is called like a normal distribution with mean value of 80, standard deviation of 5, and it's truncated from 50 to 95. Okay? But remember, our uncertainty might not necessarily follow a normal distribution. That might not be the case. So normal distribution, that is when you have like this bell-shaped curve and your variable is clustered around this mean with equal variability on both sides. So I have this bell-shaped curve. Oops. And my variable, my cost, is clustered around this mean with equal variability on both sides. But who said that I have equal variability on both sides? It could be the case that I have a value where my probability is clustered around, but I might need my variability to be either skewed to my probability to be skewed to the right or to the left. Because, for example, maybe the probability of getting a cheaper labor is very low, like, and this would be more likely on this side. So you can actually use other distribution. But before we talk about other distribution, let me just talk about like random sampling. So here is like how like, remember I already showed you random sampling, but let's just look at random sampling. I told you the more you run your Monte Carlo simulations, the more accurate this will be. This is where I'm showing you this here. So here, this is like my Monte Carlo simulation, and like my objective here is, this is a normal distribution, a theoretical distribution. And what I'm doing, I am drawing random value from a variable that is like normally distributed. And I will see, can I like reconstruct this normal distribution or not? So like you see here was 5 samples. So I just took random, like, because you just took random samples. So I took one sample here, one sample here, one sample here, one sample here. Where's my mouse? Oh, what happened? Oh. Sorry about this technical issues. Okay, here we go. So here I just like took 5 samples. So I took like random sample, like one sample here, one sample here, one random sample here, one sample here. So you see, I cannot reconstruct this probability distribution because the frequency is this is 1, 1, 1, 1, 1. So that looks more like a uniform distribution. Now here I took like 100 samples. So now I took 100 sample, and when I do a histogram for these samples, see now I'm approaching like this theoretical distribution because I increase the number of samples. So this looks a little bit more like a normal distribution, except I have like something missing here. I have something like overshooting here. But here I have 100 sample. Like if I took like 10,000, 1,000 sample, now you see like this looks correct here on the tails. I don't have much overshooting here. If I took 10,000 sample, the frequency of my sample, like here, exactly I got like the samples that has low probability are very small in numbers. The samples that has high probability are very small in number, and most of my sample are here. Yeah. Versus like if you only take few sample, like now you see this is equal probability to this, equal probability to this, equal probability to this. Versus here, this has much lower probabilities than this one. I mean, if you don't understand much of this, that's fine, but the most important take home here is that when you do this Monte Carlo, try to do like take your samples, as many samples as you can. Like here, see at this step, this is the number of samples. So here, for example, I have 100 samples. Here I'm showing it for like 200 samples. Uh, and so this figure is built on, actually this figure is built on more than one number of samples. So try to see, make it like thousands of samples. That's when you do that, because when you do more thousands, you can sample your probability space more and you get more accurate results. So that is with respect to the conversion of Monte Carlo. But before that, just that is with this conversion of Monte Carlo. But let's get back to our different types of probability distribution. So we said like we can have like a normal distribution, but you can also have other like triangular distributions. So triangular distribution, they don't go from positive infinity to negative infinity. They just go from a minimum that you define to a maximum that you define. And then here is the most expected, the mode, like the most expected value that you will expect. So this is, so in triangular distribution is defined by a minimum, most likely, and maximum value. And this is ideal when the range is known, but the exact shape is uncertain. So I know the range, I know I will not go below, oops, I will not go below this guy, I will not go above this guy, but the exact shape is uncertain. I don't know if I will be more like skewing to the left or like skewing to the right. So here I am more skewing to the left, which means that my lowest value is here, but my highest probability that this will, like, this is my lowest estimate for this is like $2, for example, or whatever that is. But my most likely value is about like 2.5 and this is the maximum value, and the probability for this one is like almost like 0. Yeah, here I'm more skewed to the right, so like this is my lowest estimate, this is my highest estimate, but my most likely value is will be around here. So I'll be more on the high side rather than the low side. But it's not only normal distribution. So here is a normal distribution with a mu, like mean of 100 and sigma of 15. This is a triangular distribution with minimum of 80, maximum of 140, mode of 100. And this is a uniform distribution. Here, uniform distributions, these are other types of distribution. We talked about this. This is when my event or my outcome could be anywhere from here to here, but which one I don't know. I really don't know. So this is the maximum uncertainty. So here, this is like this type of distribution is when I have like the maximum uncertainty, where every value within the specified range is equally likely and suitable. And this is usually suitable when you have uncertainty and no clear central tendency. So here I have a clear here I have a clear center tendency, and here I have a clear center tendency with equal probability on both sides. Here I have and I don't really have a min or a max. Here I have a clear central tendency with could be skewed to the left or skewed to the right. Here I don't have any central tendency. Now, another interesting probability distribution is the beta distribution, and this is very flexible because beta is like flexible. It is bounded, unlike this guy which is unbounded. Like this guy, it is bounded. Like so, it will be, it's a bounded. Uh, uh, and it could be like skewed to the left or skewed to the right, and it depending on the alpha and beta value, and I will talk about this guy. Like I said, it could be bounded or could be also unbounded. Yeah, uh, uh, it could, like in that case, sorry, in that case it's like it is bounded. So here it's like in that case it's bounded. Yeah, it's bounded from 80 to 100. Yeah, and based on this alpha and beta shape, you can make it I will talk more about this. Yeah, I will have a special slide for this. And then you could have other distribution like log normal distribution. So log normal distribution, that is positively skewed distribution used for variables that are always positive and prone for occasional range variation with high probability of small value. So for example, when we model hydraulic conductivity, we use log normal distribution because it varies by orders of magnitude. Yeah. But in cost estimation. And that is here, this is like your final outcome. Remember, like your final forecast outcome for the frequency of like your cost. It does not necessarily, like you see here, this is a normal distribution. Your final outcome might not necessarily fit any of this distribution. Like you see here, your final outcome, it does not fit like this guy for sure. I put like this guy, it does not fit a triangular distribution. It does not fit uniform distribution. It does not also fit like a log normal distribution, like see this green thing here. And it does not also fit like this beta distribution. So your final outcome might not fit any of this parametric distribution, and you might need to fit something called like a non-parametric distribution. So this is a simulated sample like this here, like this guy here. Yeah. Uh, uh, um, this would be like your simulated sample. So here, this is like the beta distribution. So the beta distribution, you have like alpha and beta. So if beta is equal to 0 and alpha is equal to 1, you get a normal distribution. If beta is equal to 1 and alpha is equal to 1, you get like this red thing here, like Laplace distribution. If beta is equal to -1 and alpha is equal to 1, you get a uniform distribution. On this side here, if beta is equal to 1, so here like this is for the Laplace distribution. So I'm fixing beta is equal to 1, and then I'm putting different value of alpha. If alpha is equal to 1, you get no skewness. Yeah. So it is like you have like this central tendency here and equal probability on both sides. If you get alpha is equal to 10, it's more skewed to the left. If alpha is equal to 0.1, for example, that would be more like skewed to the right. Yeah. So that's like if you want to use this beta distribution. Here, this is just like a summary of like some distribution and with example and where you can use it for in what situation. Again, like you can pause the video and look at these guys. Deterministic, there is no uncertainty. The value is fixed. So here, these are probability distribution. My value could vary from here to here with this likelihood for each of these occurrence, and here is my maximum likelihood versus deterministic. This is just one value. Yeah. So permit cost, for example, is fixed, $5,000. Yeah. Like log normal, for example, report costs average 200, but can sometimes be as high as 200. 2000, like you see here, is like one order of magnitude difference. So if you have something that's like one order of magnitude different, then you use like a log normal distribution. This is beta. Like this is like a normal distribution, similar to normal distribution, but you have more control over it. And this is like a triangular, and this is uniform. There could be other types of distribution, like exponential, for example, or whatever. Okay, so here let me just let's see how we are doing in timing. I think the timing is good. Let's just summarize these steps. So the first step, you identify key cost driver. Here I'm identifying 3. In your project that could be 300, depending on what are the, could be you have like 300 uncertain items and maybe 10 deterministic items, or it could be all of them are uncertain, or all of them are deterministic and just 1 or 2 items are uncertain. That would be depending on what you're doing. For each of these one, you select a probability distribution that you think most uh, so here for this equipment, I have this probability distribution because that is very uncertain. It could be anywhere from 20 to 100, and I don't know which one. Versus this one here, like for my material, just to summarize, I have a central tendency, and it could be either to the left or to the right of this, like to the left of this central tendency or to the right of this central tendency. It has an equal probability. Versus my labor, it has like a minimum and a maximum, and my most it will be most probable toward like this guy. And then you just select like a sample from here, a sample from here, a sample from here. That would be one of these guys, and then you calculate the cost. Then you select like this sample, like this sample, like this sample, and then you calculate the cost. And if you took like this cost and like plot it by the frequency of occurrence, and you plot it like this is a histogram. So basically, the value that has from 150 to 155 are many, like one. From 155 to 160 are about like two of them. From here to here, about maybe three or four. From 170 to 100, like 75, like these guys are about like, I don't know, five or six. These are the values. Like if you counted the values here, that uh, has like most occurrence would be around like your mean cost. And then you can do this cumulative probability distribution for decision making. Okay, so that is all for this lesson. In the next lesson, I will show you like a case study, like we will apply what we learned here to a farm. So we will like look at the uncertain items, and I will show you like how to do this with Python, and then there will be another additional lesson, like an optional lesson, which you see how to do this with Excel. And actually doing this with Excel is very simple. Like if you watch this lesson, you will see that it is very simple to do. Okay, so see you in the next videos.